our next task, our next job is just a little bit more complicated. Now what we want to determine is the brightness on that far away photoplate 2. Right? This is called sort of the far field. Now, we know the standard procedure for calculating these things because we calculate it just like we would for light, because we've seen that electrons follow exactly the same diffraction patterns in the G.P. Thomson experiment. So we can treat this as though we were doing a light calculation from our course on waves, and the way we do this type of a calculation when we have waves passing through some sort of a slit-like situation, which is what this is we use Huygens principle. Now, Huygens principle consists in these tiny little wavelets, they're called. So what we do is we consider our slit. So here's my x-axis, and this is x equals 0. And we have these waves, right, that are coming in from my source. And my source is down here at some angle theta naught, right? And what happens is the waves come and they arrive along this path towards the source. And as they arrive, they are arriving, moving up and down, up and down. And what they do is they create an up and down, or a wave-like source, a wave-like point-like source, where they impinge on the slit. So for instance, right here at the origin, we can think of these Huygens wavelets as waves that are emerging from a point source at that location. Now, it's not just that location, though. It's all the locations where we actually have these little wavelets arising, right? And they then have these little waves that then are spreading outward from them, right? And they, of course, are occupying over my entire slit. And what determines then the brightness as I am far out over here somewhere on my observing screen is the superposition or sum of the effects of all of these outgoing point-like sources. That's your basic Huygens principle. Now, I'd like to consider one particular source, and then, of course, we have to add all of them up. So for that particular source, I will choose one that is up here at a distance x from the origin. So I'll be looking at this source. And we have to determine for this source two different things. We have to determine, as with any wave, there's an amplitude associated with it, and there's a phase. For the amplitude, we know the basic relationship, right? Which is that amplitude of a wave goes like the square root of the brightness. Now, of course, it's not a strict equality, right? These types of calculations are always done with as a proportion, with some kind of proportionality constant, but that amplitude then is proportional to the brightness, the square root of the brightness, so we actually can determine it. It goes like the square root of, and again, I'm just writing proportionality constants, so I have to take the square root of this brightness, the square root of a Gaussian, well, square root raises something to the 1/2 power, which becomes a product in my exponent, so it's e to the minus x squared now divided by 4 sigma squared. So that determines for us the amplitude of a given Huygens wavelet that is generated once I've passed through my filter, right? Now, the second thing we have to determine is the phase of these little oscillating wavelets as they then begin to spread out into the far field. And the phase is a little bit more tricky. The reason why it is a little bit more tricky is that if we consider, for instance, our point up here at x, right? The waves that came from the source had traveled along this line, and you will notice it's a slightly longer distance to the source. To determine that difference, you know the standard procedure for these wave slit interference calculations. We drop a perpendicular like this, and that perpendicular, by the way, if you recall, is when the source is very far away, as is ours. It's actually a segment of a circle of constant radius r. So we actually know that this path length up to this point here and this path length up to this point here are equal to each other. The tricky part is, as you can see, there's an extra path length, there's an extra phase that this wavelet at location x has relative to the origin location. And that phase then will play an important role in determining the behavior of the waves out here in this far field, and we need to determine it. So we've got this phase here. that as a function of position x. And that phase delay is associated with this extra path length that I've traveled. So the phase delay associated with it will be the path length, which I will put here in my numerator, divided by the wavelength, which then will count up the extra number of waves that have had to travel, and then we multiply by 2 pi because we want always our phases in radians. The big question is, what is this extra path length? That is this distance. And if we follow the geometry here carefully, right, if this angle is theta, here, if this angle is theta, that tells me that this theta naught, this angle would be the complement of theta naught. And because now I have this additional right angle, this angle would be theta naught, the complement of the complement. And so this extra path length is theta naught, my angle, the sine of my angle, so it'll be times sine theta naught, times then the hypotenuse here of my right triangle. And that hypotenuse is my distance x. So that is the additional phase information that I need. Now, we can begin to use some of our quantum mechanics and to simplify this a little bit. This will be for lambda. Of course, we know from our quantum mechanics that is just Planck's constant divided by the momenta of the particles as they come in. And we know those momenta because we know the energy of our source. So now we can simplify. You want to notice that the momentum is in the bottom, so that will come up on top. So there'll be a momentum on top, which then, oh, this is interesting. When the momentum comes on top, I can combine it with sine of theta naught. We'll come back in just a moment as to what that represents. So I've taken care of my p. I've taken care of my sine theta naught. I am substituting in for my lambda, so I don't have to worry about lambda. Oh, I've still got a factor of x, and I've got my Planck's constant. So I'll multiply here by x. And now Planck's constant is in the denominator, but it has a 2 pi over it in the numerator. So that's the same thing as an h bar. So that gives me my phase. And why I was kind of interested and why this catches my attention is that momentum times sine theta naught tells me something very interesting. Because I know my particles, right, are traveling along at this angle theta naught with respect to the horizontal. And if I take their total momentum p times the sine of theta naught, that is telling me the momentum that they have in the x direction initially as they come from my source. So I will call this the x component of the momentum, comma 0. That is their incoming x momentum. They come in with some momentum along the x direction. Our task is really to figure out what happens to their outgoing momentum once they've passed through the filter. Now, one last mathematical point to make before we can go on with our analysis. While we're learning and becoming familiar with these quantities, you'll notice I have a momentum in the x direction divided by h bar. And that's a very interesting combination. I want to recall for you one last time this key connection. You know, right, that momentum, as we had just said, was Planck's constant over wavelength. But wavelength itself, when we use sort of the more grown-up quantities like wave vector, and instead of using regular frequency, we use angular frequency in our wave theories, lambda, you will recall, is actually 2 pi divided by the wave vector k. So momentum, actually, when you work this through, k then will move on top into my numerator, and then I also have Planck's constant over 2 pi, which is h bar. This is a key relationship that I want you guys really to memorize. And it shows you, a very important lesson, that whenever we're thinking about momenta, right, we are equivalently thinking about wave vectors, right? They are directly related to each other. Whenever you see a momentum, I want you to think, oh, there's a wave vector k that it corresponds to. And likewise, when there's a wave vector k, oh, there's a momentum that it corresponds to. H bar is just the conversion factor between these same two ways about thinking about what is essentially the same thing. So when I see a phase here that has a momentum over h bar, I get very excited, right? Because that tells me then that my phase is related directly to some wave vector, because p over h bar is a wave vector, so I will call that wave vector k naught. So I have my phase is just k naught times x. That looks just like a standard wave type equation, and you'll notice that I am defining k naught here as the incoming x momentum, just converted into wave vector notation. And if you really want to be pedantic about it, the incoming x component is related to sine theta naught via this relationship here. Perfect. So now I know the amplitude and phase of each of my Huygens wavelets. The next thing we do traditionally to carry out the computation, to make the mathematics work out a little more easily, is to actually combine this amplitude and phase into a single complex amplitude, because then we can use that more conveniently in calculating the final superposition. Now, this complex amplitude, right, in quantum mechanics, the symbol we traditionally use for it is psi of x. So let me write that Greek letter psi of x. It's in traditional wave theory, it's called the complex amplitude. In quantum mechanics, we call this the wave function. It's the same idea. It's a function that describes the amplitude and phase of my wave. So it's called the wave function in quantum mechanics. And what we see is it has an amplitude and phase associated with it. The amplitude we know is proportional to this factor, so I'll write it as a proportionality constant. I don't want to, oh no. Okay, yeah, there's a proportionality constant we will deal with in a moment. Then I have the amplitude is e to the minus x squared over 4 sigma squared. And then I have to, let me actually write what I'm doing. So this complex amplitude is equal to the actual amplitude times the phase. And the actual amplitude we know only up to this proportionality constant to be e to the minus x squared over 4 sigma squared, just as I've indicated to you up here. And then the phase is e to the I, and the phase was just this k naught, which we've just defined, times x. So that gives me my wave function. It's just proportional to this quantity. Maybe even better, I will write it as equal to some proportionality constant alpha times that quantity. Now, we generally speaking in these wave type calculations only worry about things up to a proportionality constant. I, however, would like to choose this proportionality constant to define a convention so that my wave functions are actually absolutely defined, not just up to some arbitrary constant. And the way we can do that is to make a specific choice. So we're going to make a choice, right? So this is going to be a convention, by convention. Right, so we're going to choose, we're going to choose by convention alpha, so that when we write the probability of finding a particle, right, which we know is proportional somehow to brightness, right, which we know is proportional somehow to the square of a complex amplitude, right, which we know now is somehow proportional to the square of what we call actually the wave function. Oh, that's amplitude squared, complex amplitude squared gives brightness to our wave function. I want to choose alpha so that instead of this kind of chain of just proportions with potentially arbitrary proportionality constants, instead of that, we have the following. I would like to choose alpha so that always the probability distribution in X is actually strictly equal without a proportionality constant. I'm going to choose the normalization of psi, this a constant prefactor, so that probabilities are actually given directly as the square of my wave function. And in this case, we've actually already figured out what would make that happen. right? This shows you that my wave function, the magnitude of my wave function, is just the square root of my probability. So in this case, the magnitude of my wave function is a product of a magnitude and a phase. The magnitude is the square root of my probability. My probability was, where was he? He was normalized right here. Here's the probability, right? 1 over root 2 pi sigma squared times a Gaussian. So when I take the square root of this, I will get this, instead of a 1/2 power, will be a 1/4 power. And the square root again of the Gaussian just divides the exponent by another factor of 2. So then, using that, this will be what we saw up above, 1 over 2 pi sigma squared, which in the probability was to the 1/2 power. When I take the square root, it becomes the 1/4 power. Then I have the Gaussian part of the amplitude, which in the probability is e to the minus x squared over 2 sigma squared, but now because I'm taking a square root, that becomes 4 sigma squared. And that then is the magnitude of psi. But any complex number has a magnitude and a phase, and we've already determined what the phase of psi is. It is this phase factor here, my e to the I k naught x. So that is for our example, right? The wave function can have different values, of course, for different examples, but in our example, we have this value for the amplitude and phase then of my Huygens wavelets. I understand now a relationship between this wave function and the probability. My next job is to figure out what the superposition of all of these complex amplitudes will do and how it will behave as it impinges upon my photoplate out in the far field.